Okay, thank you. So I'm Patrick Lee, and joining me here is Simona, and we are both from Saint-Gobain Research Paris. And for the past year, we have been diving deep into the world of causal inference. So first of all, thank you, the organizers, for giving us this opportunity to share our journey, and especially the use case on Glasswool production. This is a collaborative work with Judith Abekessis, and she is a researcher in causal inference in Inria. So for today, I will kick off by introducing what our business is, so it's Glasswool. And then we will go into unraveling the mysteries of causal inference. And after that, I'll let Simona guide you through the use case. So, what is Glasswool? Glasswool, so first of all, Saint-Gobain is a construction material company, and we make a product called Glasswool under the brand name Isover. So Glasswool is a superstar when it comes to thermal and acoustic insulation, and a hero for fire protection. It is made from recycled glass that we call cullet, sand, soda ash, and limestone. You can find it everywhere, in the roof, under floorboards, between walls and partitions. And before we deliver them to our customers, we characterize them rigorously on the density, on the size, the color, elasticity, and most importantly, the thermal conductivity measured by lambda coefficient. So the lambda coefficient is a measurement that measures the heat transfers between materials, in the material, sorry. And you can imagine during summer, for instance, you want your house to be cool. So you want less heat to transfer from the outside into your home. And during winter, you want the other way around. So you want to keep your house a little bit warm, so you don't want the heat to be released to the outside. And fun fact, the best insulator is immobile air. It only has a conductivity or lambda coefficient of 0.03 watt per meter Kelvin. So now you know about the Glasswool, but how do we make Glasswool? So first, we mix the raw materials, the sand, the cullet, soda ash, and limestone, and we melt it to a temperature of 1,450 degrees Celsius. And the next step is very much like making cotton candy. But instead of spinning sugar, we are spinning glass. The melted glass is fed into a rapidly spinning metal cup that we call spinner. And this spinner, as it spins, will spin out the fiber. When this fiber is in contact with air, it will cool down, and we spray what we call the resin binder to make it stick together. And that forms a mat wool, and this mat wool is then heated at a temperature of around 200 degrees Celsius to polymerize the resin so that it gives its strength and stability. And then we cut, package it into rolls and slabs, palletize, and store them for use. So for a manufacturing plant, two things matter. The first one is stability in the production. That's why they have a lot of sensors installed everywhere to monitor the processes 24/7. The second one is quality. The product quality has to always meet the norms. So with the data flowing in, we thought, why not use this data to optimize the lambda efficiency? So imagine you can just tweak the 1 or 2 parameters and you can see a direct impact on the product quality. So to do this, the first step is to build what we call a product-centric database by gathering data from the processes, so from the sensors, the raw material data from the Glasswool production, from the Glasswool composition, and the physical properties, production data, and the quality data together. And then the second step is to define the target. So you have here a curve that is called Larkin curve. It is a semi-empirical law that dictates the relationship between lambda and density. In theory, what it means is that if you want to build a good insulator, so low lambda, you need a higher density. But in practice, that's not always the case. So you have the blue dots here that represent the real measurements from our products. And you can see, first of all, 4 clusters that correspond to 4 different categories of products, lambda 32, 34, and 37, and also lambda 30. And you also observe that there are some dots that are above the curve and some under the curve. So when it's below the curve, we call them the good products. Why? Because we can achieve the declared lambda at a lower density, so it costs less material to produce. When it's above the curve, we call them the bad products. Well, it's because we need more material to build them so that they can achieve the declared lambda. So previously, we have been using machine learning models, classic machine learning models, and interpretation tools to recommend some parameters. But the question that we get is, so what is the causal link between this recommended parameter and the target? We hit a wall. We don't know what to say because machine learning models only find correlations. So we need something better. Take the classical example of shark attacks and ice cream sales. So a machine learning model can very easily learn from the number of shark attacks and predict on ice cream sales. But do they actually have a causal link between them? Well, of course not. There is a hidden factor here, summer. Summer is a confounding variable that affects both. And because we're not taking into account this confounding variable in the machine learning model, it distorts the true relationships between them, and it leads to misleading conclusion. So enter causal inference. Causal inference is not new. It has been introduced in the 1920s by Neyman and Rubin. Its purpose is to identify a cause and effect relationship. It is very much used in medicine, economy, social, and political sciences, where it is hard to conduct controlled experiments, where you want to only study the effect of one treatment, but controlling other parameters in constant. But don't get me wrong, it is not a method to replace the gold standard methods like RCT, randomized control trial, or A/B testing. It is just an alternative in case where you don't or you can't actually conduct this gold standard methods. And of course, causal inference does not come freely. It comes with some assumptions. The first one is SUDWA. So SUDWA states that the potential outcomes of one unit or one individual should not be influenced by the treatment assigned to another unit. And this assigned treatment should also be consistent, meaning that, for instance, if your treatment is a dosage of a drug, then this dosage should be the same assigned to all the individuals. And then you also have ignorability or confoundedness, where the treatment assignment should be randomly distributed to all, regardless the background variable. And this this leads to the positivity, meaning that for each background variable, you should have the treatment assignment of being treated or not. The potential outcomes framework is the framework that we use when we carry on a causal inference study. It is also called Rubin-Neyman causal model. So in this framework, we assume that for each individual there are 2 potential outcomes. One is if it is being treated, and one is if it's not. But if you think about it, in the real world, that's not possible. You cannot have a treatment, you cannot have the same individual being treated and not treated at the same time. So that's why we talk about potential outcomes, because we are actually just estimating this. And this gives us the possibility to calculate the average treatment effect when we look at the group level, and conditional average treatment effect if we want to look at the subgroup level. So the method that we use is called double machine learning. So I provide you these reference here if you want to dig deep into the math. But it actually presents two main points. The first one is that if you have a good performance in prediction, that doesn't mean that you will get a good performance in the causal estimation. And the second point is that we want to debias our data as much as possible. That's why we are using, we are training two models. One on the, one to predict the y using the confounding variables z, and the other one to predict the t with the same confounding variables. So you have the EYZ and ETZ. And then we calculate the residuals of these two, the y hat and the t hat. And that gives us the y hat equals to t hat theta 0. Theta 0 is the average treatment effect that we want to find. So we can do a regression on it to get the value. And so that's the theory. Now let Simona guide you through the case study.
Okay, so thank you very much for all the theory. Now we can dive a bit in, the use case. So what we did at Saint-Gobain to apply causal inference instead of the classic machine learning models. So when we have a causal inference workflow, we have some main things we have to do. The first is that it's not as the machine learning model, but in causal inference, we answer to a precise causal question. So when you want to do this type of study, you need to go to the expert. You need to understand what is the question they want to answer. For example, in our case, it was, what is the effect of using a spinner, which is a part of the process that Patrick explained to produce the Glasswool. So what is the effect of using a spinner used twice as often on the Glasswool quality, meaning on the delta larking you've seen before? Because at the plant they have the feeling that this spinner age, to the age of the spinner, may affect the quality, but how much they didn't know it. Then, once we define a causal question, we can go with the first main steps of causal inference. The first is building the causal graph, which is the most time-consuming part because it means taking into account all the variables of the model. Then there are the identification and the estimation part, which are the more theoretical, meaning that we need to determine the variables to set to isolate the causal effect. And then we need to estimate the causal effect with, for example, the double machine learning methods that Patrick explained. Then, once this is done, we need to do the sensitivity analysis to study if the model is robust. If the sensitivity analysis, which is at the end, is correct, then we can provide recommendation to the plant. As first part, exploratory, we start with the causal graph. With the causal graph, the first part is always to talk to the expert to model the process. So we ask him what is the treatment, what is the outcome, and what are all the confounding variables in the system, which of course, like for shark attacks and ice cream, it was summer, but it must be, you have to be very detailed, because if the graph is good, the model is good. If you forget some confounding, then it will not be taken into account in the model. Then you create the dataset, as we do for machine learning project. And then as exploratory analysis, you can see if there are some correlation. It gives you a hints of what is hidden behind. For example, for our use case, we went to a plant, we took 3 years of data, and we divided in 3 different product types. So according to the lambda, we have lambda 37, 34, and 32, which are 3 different products. So in typical machine learning, you plot the y and the x, and you see if there is some regression. If you do study, and then maybe you can find you can do some analysis. Here, what do you find? If you go to the business with this graph, you will not find as much. Maybe in lambda 37, if you stretch a bit, you can say that there are correlation, but even I don't know if there are true correlation. And then for the other, we don't see much. And even if we see correlation, is there a causality link? This is the question we want to answer. So now I will give you an overview of what does it mean to build a real causal graph from the plant. So what we showed before with summer, ice cream, and shark attacks is very easy. Here we go into the details. So it means that the starting point is always the outcome, you can see below, and the treatment, in red, the spinner age. Then you talk with the expert, and you try to find all the confounding variables and all the links. Always to keep in mind that you need to answer to a specific question, meaning, I repeat it, what is the effect of the spinner age on the delta lambda, on our outcome? So this is an iterative process, meaning that you don't expect to be perfect in the first time, but you draw a first draft, then you iterate maybe one session later with the expert, and you go on and you go on. Your code, your way of working must be also flexible to adapt to new things. For example, when you present the results, they can ask you, okay, but did you take into account this? And the answer maybe is no, because it was not in the graph. So you have to come back and draw the graph and add some links that it can modify the hypothesis and so on. So here, just to let you understand, here all the confounder are, it's anonymized, the graph for intellectual property, so this is why you don't see, but there is some hidden parameters of the sensors behind every bullet point. So once you have the graph, you can then start the identification part. So as a tool for the identification, meaning that you want to verify if the hypotheses are corrected, the hypothesis that Patrick explained before. For the hypothesis, for example, one thing that must be done is that there are no cycle in the graph, so there are no loops. So when you have a for graph is easy, for curve is easy, but when there are multiple it's complicated, so there are some open source tools. What we used for also to explain to the experts what we were doing was to use DAGitty, which allows you to, in a very nice way, to draw and visualize causal diagrams. You can also move the points, it's very nice, and at the end, it tells you, okay, if this is your treatment and this is your outcome, you can do causal inference. Otherwise, the hypothesis may be violated and you cannot do causal inference. So I recommend this is open source tool. But we did everything then in Python. So what are the main steps and which is the library we used? So for our study, we used the DoWhy, which is a known framework library open source in Python to do causal inference. And there is also a great documentation that I recommend to dive from a more software point of view to the implementation of causal inference. So the first step is to instantiate a causal model. The input you must have is your data frame, which means really the classical Excel table we used to work in. Then you have to define on your data frame the column which correspond to the treatment and to the outcome, and you have to have the graph. The graph, so this is what I shown before, can be a string where you have point 1 direct point 2, comma, point 2 direct point 3, etc. It can be very long, but it's just a string. So it's very easy to model, and we just do why. Then you can do the identification part, which is what was done by DAGitty before on Python, just calling the identify effect part. So even in this case, DoWhy has a lot of methods, they are implemented, and finally it tells you if you can go or not on with your causal inference work. So once the identification, you validate the graph, in the analysis, then you can do to the third part, sorry. In the third part, you do the estimation. So the average treatment effect, so it's not the regression of a variable, but it's the estimation of the effect and the conditional estimation. Also, in this case, it's done by DoWhy with the model you have instantiated, and you call the estimate effect method. So DoWhy is very flexible because it integrates all the methods of EconML, which is another open source tool, open source library in Python, which implement a lot of causal inference method, because according if your variable is continuous or not, the treatment is continuous or not, you can have different methods. In our case, we use the linear double machine learning, but you can have way more, and they are mostly implemented in EconML. So you can use DoWhy calling EconML, which makes life very easy, because then you define your treatment, your outcome, how you want to model, and then you can have the estimation effect. So this is the estimation, but then you have to validate your model. As I said, to validate the model, we have to do a sensitivity analysis. What does it mean? I have my model, and then with the input parameters, and then I change a bit the input parameters. For example, I can add a random cause, a placebo treatment. I can use just a subset of data, and I want to understand if the model is robust or not to this little variation, because we would like the model to not be sensible to all these variation. This is why it's called sensitivity analysis. So we do the analysis for each type of product for different hypotheses, and if the model is not different, it means that p-value, so the threshold effect, will be greater than 0.05. In our case, the model was robust because every value was greater than 0.05, and so we can provide the recommendation to the plant. And also this, it's implemented in DoWhy. This is why I sponsored this package, because it's very well done. And we can just say the method we want to implement, for example, here in the example, the placebo treatment refuter, and then it gives you the p-value. So if you have your graph, your data frame, and you know your process, you can go on. So now we go back to the plant and we say, okay, we found something. We found, for example, that in average for all the product, a spinner that has been used twice as often typically reduced quality by a factor of 1.6. Because here, if the quality in the axis is higher, it means the quality decrease. And we can be very specific. And it's not just a correlation as in machine learning, but here there is really a causality link. So we are sure that the decrease of quality shown here, we see for all the product we are above the threshold of 0. It means that there is an effect and it's causal. For example, in the first graph for Lambda 37 product, we really go in the detail of the product. We see here we have 6 different products. It means that they are different for the size or the width, etc. And we say, for example, for product 1, that the quality of using this type of spinner decrease of 2.1. For example, for Lambda 32, for product 5, we are about 0.8. So really, you give a recommendation more specific to the plant so they can do what is then economic analysis after. That, for example, to optimize when they need to change the spinner or not. So this is what we did, and what are our conclusion is when we should use causal inference. So thanks to this study, we understood that if we want to understand if correlation implies causation, we can use causal inference. DAGitty and DoWhy we strongly recommend. They have a user-friendly API that you can use for causal inference. And the key principle we found out, it's not very new in data science, is that if you garbage in, garbage out, meaning that at the beginning, for example, we had a lot of data, but they were not so clean, and finally the results were not very comprehensible by the plants. And finally, when we spend a lot of time cleaning the data and the graph, then also the results were better. So as in all data science, causal inference as the main issue. And the challenge as data science is always data quality, but also to have an expert available to draw the graph. Because, for example, we are not material scientists, so we don't know how the plants work, how the sensors are connected, and we need to be an expert available to talk with us. But the benefit of having this expert available is also that you can really communicate better. For example, in data science, for machine learning, sometimes you have your data set and you just ask what is the column A, what is the column B, how do I link column B, column C, and it's very time consuming here. The fact that the expert is implied in drawing the process, I think it is part of his part, and it becomes also more active in the results. And here, we just give you all the library we have tested and the book we read for the talk and for the work. Thank you.
Thank you, Simona and Patrick. Any question?
Yeah, thank you. Very exciting. And I want to ask if you already built a graph, and you also already defined a lot of confounding variable between the x and y. I mean your target outcome variable and also your treatment variable. What if you have the data, but you don't have the information regarding the confounding variable? Then how can we deal with it?
You have to have the information about the confounding variable. The input is not just the data in machine learning. You cannot leave the data alone because really the input is the data plus the graph. So when we also go to the business, we say, okay, do you have people that can draw the graph? Do you have something that we can have the information, etc. We know that there are also some study about causal discovery, meaning that you just have the data frame and you try to infer the graph from the data with statistical independence analysis, for example. But we didn't try, or we know that it's very complicated, and if you don't have all the confounding variable in the data with a lot of sample, it will not work so well. Do you want to add?
So just on causal discovery, the problem is that if you have too many variables, then the number of computation becomes exponential. So you can only solve a problem that is not that does not have too many columns.
Thank you for sharing this case study. I have a question about the estimation of conditional treatment effect. From my experience, for example, using Causal ML, you can achieve the different results depending on what type of learners do you use. It's T learner, S learner, X learner, you name it. Do you maybe have experience in this project on applying the different types of learners to estimate this conditional treatment effect?
Yes, we tried different things, and basically since we have continuous treatment, continuous outcome, the linear double machine learning, finally it was where we had the most, the results that were better. We tried also different things, but the results were not so good, so it was very empirical what we tried a lot, and then let's see. And yeah, and it was also very fast to compute, because for others it will take a lot of times to have results, and here it was quite fast at the end. So yes, I think it really depends on the input and how many data you have, as always. Do you remember other stuff?
One last question, and if you have more questions, okay, maybe we can dedicate a couple of.
Thank you for the great talk. I was just wondering if you did try any other libraries before converging to this set of libraries. And how did you go about convincing the business and the top management that Causal ML is the answer in this case? Because often convincing people about trying new methods is not as easy as it sounds.
We are still convincing. I believe that the more you do, the more people know about the work, then that is a way to kind of like start convincing people, because when other groups also heard about your work, then that helps in convincing. So about your question regarding did we try other packages, we did try, for instance, written here Causal ML. So when we try it, the first thing that we check is the result given by this models coherent with what the expert expects. With Causal ML, we kind of have some very weird results. So and then we try on DoWhy and EconML. It gives a more stable and more coherent result, and that's why we stick with those.
So actually, we have time for more questions. I was a bit wrong, so.
I just want to add, and also the book we read are linked to DoWhy, and the 4 steps you study, you find it in the code, and it's quite satisfying. At least you find the same structure.
Thank you for the presentation. In your study, I think in the final result, you just presented average treatment effect and not a conditional average treatment effect. Have you tried to assess whether there is heterogeneity in the treatment effect, and how much and which, if there is a sensitivity to different dimensions of X, and how do you conduct such a sensitivity analysis to heterogeneity?
Okay. Yes, we did. When we presented the results, for example, here we present for the different product. So for example, here you see the product description. It's already conditioned on which product. So product 1 of a certain size, etc. And we also presented, they are not here, but for example, for other characteristic of the plant, to say, okay, but what about I change the confounder 1? And so we change the we change the how we presented the results. Yes, we really try to answer the question as the experts want.
Thank you.
One last question? No? Oh, okay. Thank you. Go ahead. Sorry.
Thank you for the talk. Just curious, the application is very real world, right? The one you talked about. I was wondering if you ever actually follow through after what happened with the recommendation and went back and checked, see the real output versus what you recommended and try to optimize, or how it went.
The answer is very short. So this is very recent. We just show this information, this recommendation to our customers. The next step is for them to really do the trial on the production line and then to confirm with the results that we have found. So that's the next step.
So thank you very much.